Today on AI Paper Slot, we are tearing directly into DreamX-Phi 1.0, action-conditioned video world model for robotic manipulation. This paper dropped on August 13th, 2026, and if you are an ML engineer tuning in, the core insight right up front is that this is a forward dynamics model. It is built on top of the WAN 2.2 Ti2V 5B video diffusion transformer.
Right, yeah.
So you feed it an initial RGB frame, a text instruction, and a prescribed bimanual action trajectory, meaning the exact end-effector poses, and it predicts the resulting future video observations.
And this is actually a massive distinction in the world model space.
Mm-hmm.
Because, I mean, we've had models that can generate highly photorealistic video for a while now.
Oh, totally.
But if you work in robotics, you know that photorealism is absolutely not the same thing as physical faithfulness.
Yeah.
Like a standard video generator might make a beautifully realistic cinematic video of a robot arm moving.
But might just move the wrong arm entirely.
Exactly. Or say you have a robotic arm reaching perfectly for a coffee mug. The trajectory is flawless. But the second the metal gripper closes, the mug just, seamlessly morphs into a soup bowl.
Right. The object permanence just totally breaks down. The video looks perfectly photorealistic, but the physics are completely hallucinated.
Yeah. And DreamX-Phi 1.0 solves this physical faithfulness problem by explicitly injecting rigid body SE3 geometry directly into the transformer's attention mechanism.
Which is wild.
It is. They do this using a PRoPE style encoding, and then they back it up with heavy auxiliary supervision from SAM3 And V-JEPA during training. That basically forces the model to respect the scene geometry.
Okay, so to understand why this model succeeds, where others just, hallucinate pretty pictures, we have to look at the bottleneck in standard video diffusion models, specifically how they usually handle action conditioning.
Right. If you look at current world action models, or WAMs, they have a very specific and frankly kind of flawed way of telling the model what the robot is doing.
Yeah, they usually just compress those actions into low-dimensional tokens, right?
Exactly. They compress them, or they use generic control embeddings, like passing the actions through a multi-layer perceptron and injecting them via cross-attention or feature-wise modulation.
So you are taking the complex, continuous 3D path of a robotic arm over time and squashing it down into this dense, abstract vector.
Yeah, which, it tells the model what the action is, like a semantic instruction, move forward and grab. But you completely strip away the continuous rigid body geometry of how that end effector actually moves through 3D space.
And for anyone who needs a quick refresher, SE3 is just the mathematical group that handles 3D translation, moving up, down, left, right, and rotation.
It's the literal math of how a solid object moves in space.
Right. So by squashing that into a token, standard models are just throwing all that math right out the window.
They really are. When you squash those actions into a dense vector, you're forcing the latent space to implicitly learn the laws of kinematics entirely from scratch. The transformer just sees these numbers and has to guess how they correlate to a physical arm moving across the image patches.
And that is where PRoPE comes in, right? Projective relative positional encoding.
Yeah. PRoPE was originally designed to handle camera viewpoints, allowing models to understand how a scene changes when a camera moves. But here, the DreamX team adapted it specifically for bimanual robot arms.
Okay, let's unpack this, because standard token injection is essentially handing a video generator a text prompt saying, move the left arm 5 centimeters and, crossing your fingers.
Hoping it figures it out, yeah.
Right, hoping the latent space has memorized enough robotic physics to make it work. But PRoPE is like hard-coding the exact 3D wireframe math directly into the attention heads. How does that structurally change the transformer?
Well, structurally, the transformer takes its attention heads and partitions them into fixed, contiguous groups. So it assigns specific groups of heads exclusively to the left arm and other groups to the right arm.
Oh, interesting.
Yeah, and it establishes a shared coordinate system relative to the initial pose of arm 1. Then, instead of just passing in tokens, it injects the relative SE3 transformations directly into the attention mechanism.
So it mathematically modifies the queries, keys, and values based on the inverse geometric map of the end effectors.
That is exactly what is happening. A token pair in the attention matrix is now coupled through relative rigid motion.
So the spatial relationship between the image patches is governed by actual physical kinematics rather than letting the model guess.
Right. If the arm moves 5 centimeters in the SE3 data, the attention mechanism inherently understands how that translation shifts the visual patches, because the inverse geometric map is modifying the attention weights directly.
I do have a technical question on the implementation here, though.
Sure.
Because an SE3 transformation elegantly handles 3D translation and rotation for the arm itself. But a robot gripper's open or close state is just a 1D scalar value, right?
It's literally just a number representing how wide the fingers are.
It's not an SE3 matrix. So how does the model mathematically handle the gripper in this highly rigid geometric space?
That's a great point. Since the gripper state is just a scalar, it has to bypass that specific SE3 multiplication. You can't just multiply a 1D value into a 3D rotation matrix.
Right, the math would just break.
Exactly. Instead, the gripper state is injected separately as a learned per-arm bias. It's added directly onto the corresponding attention heads after the inverse geometric map is applied.
Ah, okay.
Then those modified heads are concatenated, projected back to the original model width, and added to the pre-trained self-attention output as a residual branch. It's a remarkably clean way to combine continuous 3D geometry with simple scalar state variables.
And without breaking the pre-trained visual backbone of the WAN 2.2 model.
Exactly. It keeps the core generative path totally intact.
That makes a lot of sense. But if we think about the end goal here, getting the robotic arm to follow the exact math is really only half the battle.
Oh, for sure.
Because if the robot arm perfectly executes an SE3 trajectory, but the wooden block it tries to pick up just phases straight through its solid metal fingers, your simulator is entirely useless.
Right, and this exposes the core vulnerability of training video models for manipulation. If you have ever trained a diffusion model, you know that the flow matching objective, which is how these models learn to map noise back to clear video, has a fundamental imbalance when you apply it to robotics.
Because standard flow matching just looks at the overall pixel error across the entire frame.
Yes, the objective is optimizing over the entire pixel space. But in a typical robot manipulation video, the robot arm and the specific object it's interacting with occupy a tiny, tiny fraction of the total pixels.
Like, what, maybe 5% of the frame?
Basically, the vast majority of the frame is just a static background. The table, the walls, the floor, maybe some shadows.
So because flow matching averages the loss, a model can achieve a fantastic loss score simply by perfectly rendering that static background.
While totally botching the complex contact dynamics of the gripper actually touching the object.
So if the model renders the texture of the wallpaper perfectly, the optimizer gives it an A+, even if it completely forgets how physics works for the one tiny coffee cup the robot is actually trying to grasp.
Exactly. It inherently rewards global visual quality over local physical accuracy. So to solve this, DreamX-Phi implements a dual-pronged object-aware supervision strategy during training.
Okay, what's the first prong?
First, they tackle the spatial focus. They use offline SAM3 masks, that's the segment anything Model 3. Before training, they run SAM3 over the dataset to isolate the manipulated objects.
And then during training, they use those masks to dramatically reweight the flow matching RGB loss.
You got it. Suddenly, the model is heavily penalized for errors in that tiny contact local region.
So you are artificially forcing the optimizer to care disproportionately about the object. But I understand V-JEPA is acting as the second prong here for temporal consistency.
Yeah, the video joint embedding predictive architecture.
Right. So how do you mathematically force the object to stay the same shape across time once the robot starts moving it? Are you just matching the pixels frame by frame?
Well, no, you can't just match pixels frame by frame because the object changes perspective, it gets occluded by the robot's fingers, the lighting shifts. Pixel matching would fail immediately.
Oh, true.
This is where V-JEPA comes in. They use a frozen V-JEPA teacher model. They extract deep features from the student model and the frozen teacher. But instead of matching those features directly, they align the gram matrices of those object features across both space and time.
Okay, so aligning the gram matrices means you are matching the relationships between the features rather than the raw features themselves.
Precisely. A gram matrix computes the inner products of the feature vectors. It captures the correlations. By matching the gram matrices, you decouple the student from the teacher's exact feature basis.
Meaning the student doesn't have to perfectly mimic the teacher's internal representations?
Exactly. But you force the structural relationships of the object to remain identical. It stops the object from mysteriously changing its fundamental shape or identity the moment the robot touches it, enforcing relational consistency.
And just to round out the physical constraints, I see they also add a lightweight depth branch using depth anything 3 or DA3.
Yeah, that makes sure the model understands 3D surface ordering and object extent, which an RGB-only objective usually struggles with.
But here's where it gets really interesting. If you are an ML engineer listening to this, you are probably doing the math on the compute overhead right now.
Oh, absolutely.
Because if we are bolting on DA3 for depth mapping, SAM3 for masking, and a V-JEPA teacher on top of a 5 billion parameter 1 diffusion model, doesn't inference become completely computationally intractable for robotics?
You'd think so.
I mean, how is a robot supposed to react in real time with all that machinery running?
It wouldn't be able to. And that is where the architectural design really shines. The brilliance is in the asymmetrical design of the network.
What do you mean?
Everything we just discussed, the SAM3 masks, the V-JEPA relational alignment, the DA3 depth targets, none of that exists during deployment.
Wait, really? You just dropped the entire physics engine?
Yep. The SAM3 masks and the frozen V-JEPA teacher are strictly active only during the training phase. They shape the loss landscape, forcing the core weights to learn physical rules, but they aren't part of the forward pass once training is done.
Oh, wow. And what about the depth branch?
The depth branch is uniquely asymmetrical. During training, it uses cross-attention to read features from the RGB branch, but the RGB branch never reads from the depth branch.
Ah, okay. So you supervise the shared trunk with depth targets during training, forcing the RGB latents to learn 3D geometry internally.
Right.
But during deployment inference, you just snip the depth branch off entirely.
You snip it off, and the architecture relies solely on the heavily optimized RGB branch. It is completely unencumbered by all that heavy physical supervision machinery at runtime.
That is incredibly elegant. You get all the geometric constraints baked into the weights, but zero inference penalty from the auxiliary models.
Exactly.
But wait, even if we bypass all that heavy machinery at deployment, we still have a massive 5 billion parameter diffusion model. Even an optimized diffusion process typically takes dozens, if not hundreds, of denoising steps to generate a high-quality video.
Yeah, the fundamental speed limit of diffusion.
Right. If this is going to be a useful policy rollout environment, it has to generate features almost instantly. How does DreamX-Phi achieve the speed required for that?
They tackle that using a technique called distribution matching distillation, or DMD, to compress the multi-step teacher into a few-step student. Specifically, they use DMD combined with an adversarial GAN objective.
A generative adversarial network bolted onto a diffusion distillation pipeline. Walk us through how that actually speeds up generation.
So in a standard distillation setup, you run a slow, multi-step teacher model to generate clean future video latents. Then you train a fast, few-step student model to try and match that exact output.
Right. Pretty standard.
But by adding the GAN objective, they introduce a discriminator. The discriminator looks at the real future video latents generated by the teacher and the ones hallucinated by the student in just 1 or 2 steps and tries to tell them apart.
Oh, so the student is constantly updating its weights to fool the discriminator.
Exactly, which forces the student to produce highly realistic, physically accurate frames in a fraction of the time. But for robotics, the most crucial part of this distillation is how they handle the conditioning tuple.
Because in standard image or video generation, your condition is just a text prompt. Here, your condition is an initial image, a text prompt, and a very complex sequence of continuous robotic joint states.
Right, and during this entire backward simulation process, they keep that exact conditioning tuple, the initial frame, and the bimanual action trajectory completely fixed across all distillation steps.
So the student learns to map the noise straight to the physically accurate outcome, guided rigidly by that fixed robotic trajectory in just a handful of iterations.
Yes. So they solve the geometry representation with PRoPE. They force physical consistency with SAM3 and V-JEPA without ruining inference speed, and they distill it with DMD to run in just a few steps.
It's a massive stack of optimizations, but, you know, a world model like this lives or dies by its training data. You can't just scrape YouTube for perfectly formatted bimanual robot data.
No, you definitely can't. And the data curation here was a massive undertaking. The researchers built a heterogeneous training corpus that works in distinct phases.
Okay.
It starts with 3,700 hours of action-free, egocentric video from the Ego4D dataset.
Wait, action-free, so just headcam footage of humans doing everyday things with no robot arms in sight. Why feed human headcam footage into a robot manipulator model?
It is entirely to build incredibly broad, robust visual priors. Before a model can understand how a robot arm manipulates an object, it needs to understand how the visual world functions at a baseline level.
Oh, I see.
Yeah, Ego4D teaches the model how light works, how shadows fall, how occlusion works when an object passes behind another object. It teaches basic object permanence without the confusion of a robot arm blocking the view.
So they established the baseline reality first.
Right. And once those foundational visual priors are established, they move to action condition fine-tuning using a huge mix of robot data.
And I see they normalize all the robot data into the Lee Robot V2.1 representation.
They do, yeah.
Which includes real robot data from Agibot World and Cosmos 3 Droid, and simulated data from Intern Data and RoboTwin 2.0.
They even ran the RoboTwin simulation data through a super resolution model called DreamX Refiner, just to make sure the visual quality matched the real-world data perfectly.
That's brilliant. It's a careful escalation of complexity. It kind of reminds me of teaching an athlete.
How so?
Well, training the model on the action-free Ego 4D video first is like teaching an athlete the general laws of physics on Earth, like gravity, momentum, spatial awareness. And then the fine-tuning on the highly specific Lee Robot dataset is teaching them the specific, highly constrained rules of tennis.
That is a perfect way to visualize the training pipeline. You absolutely need the general world knowledge before the specific physical control makes any sense. The Ego 4D data gives the model the world, and the Lee Robot data gives it the action.
And looking at the benchmarks, this combination is incredibly potent.
Oh yeah. They evaluated DreamX-Phi on WorldArena, which is the gold standard benchmark for these models right now. The results are from the August 2026 snapshots, so keep that in mind as leaderboards constantly shift. But on WorldArena 2.0, Track 1.
And Track 1 is pure video prediction, right? Given the inputs, how accurate is the output video across visual quality, 3D accuracy, and physics adherence?
Yeah, exactly. Out of 31 entries, DreamX-Phi 1.0 took first place with an EWMScore-P of 60.65. They beat out massive systems like AlphaWorld and FlowAM 5 Ages. It scored incredibly high on trajectory accuracy and instruction following.
That's huge. But Track 2 is where the rubber really meets the road, isn't it? Because Track 2 doesn't just grade the video like a movie critic.
No. Track 2 tests if the model's actually useful as a functional simulator. They take the submitted world model and use it as a simulated environment to train a discrete robotic policy, specifically a Pi 0.5 policy.
Okay.
Then they take that policy, which has only ever existed inside the AI hallucinations of the DreamX-Phi model, and they deploy it in an actual separate RoboTwin rigid body physics simulator to see if it can complete a real task.
To put that into perspective for anyone listening, that is the ultimate test of physical faithfulness. If the world model's physics are flawed, the policy learns flawed strategies.
Right.
Like if objects ghost through fingers in the dream, the policy will try to ghost through objects in reality and fail immediately.
Exactly. And on the adjust bottle task, the policy trained inside DreamX-Phi achieved a 67.19% success rate, tying for second place on the entire leaderboard.
Wow.
Yeah. They also ran offline evaluations on the older WorldArena 1.0 Track 1, scoring a massive 76.88. That is over 3 points higher than the leading official entry on that snapshot.
So a policy that only ever lived inside a hallucinative video dream was dropped into a rigid, math-based physics simulator, and it succeeded on its first try nearly 7 out of 10 times.
It means the dream's physics are becoming indistinguishable from the simulator's physics.
Which conclusively proves this is a genuinely functional forward dynamics model. The fact that you can train a policy inside a diffusion model's output and deploy it successfully is wild.
It really is.
But the authors themselves note a major limitation to their own work, which really points to where this entire field of world models is headed next.
But they do, because for all of its success, DreamX-Phi 1.0 is strictly a forward dynamics model. It does not generate actions on its own. The bimanual action trajectory must be perfectly prescribed and fed to it externally by a human operator or a separate planner. The paper's authors explicitly state that their next step, their future work, is to build a joint world action model.
So to recap for you listening, what the DreamX team has achieved here is massive. They successfully fused the sheer photorealism of a 5 billion parameter video diffusion model with the strict geometric and physical constraints required for real-world robotics.
Yeah.
By using PRoPE Attention to inject the math, SAM3 And V-JEPA to enforce the physics, and DMD to make it fast, they've built a highly accurate action-conditioned simulator.
But the future they are chasing is combining the world simulation and the action generation into a single system. And that leads to a fascinating theoretical problem that I want to leave you to mull over.
Oh, what's that?
Well, if we transition to a joint world action model, where a single neural network is responsible for generating both the visual outcome and the robotic action required to achieve it, how do we prevent a new kind of mode collapse in physics?
The mode collapse in physics.
Yeah. Think about the incentives of the network. If the model is penalized heavily for generating a visually complex or messy future, like glass shattering or objects tumbling? Will it subconsciously optimize its own generated actions to take the visually easiest path?
Oh,
Like,
wow.
will it choose a lazy, timid robotic action simply because the resulting video is computationally easier to render without errors, rather than executing the robust, complex manipulation required in the real world?
So a model choosing the path of least resistance because rendering reality is just too computationally hard. That is a wild thought to leave off on. Thanks for tuning in to AI Paper Slot.